Hello, we're working on Module 2, Topic 3, Lesson 3. Last time we worked on Activity 1. We're going to be focusing on Activity 2 and 3 in this video. We'll be skipping Activity 4, Activity 5, and then getting into the assignment later. And I'll talk about which problems we're doing for that. But so far we've talked about other types of solutions, so that being one solution and no solution. So let's go and describe it before we get into this problem here. So number one, describe the graphs in a system of linear equation that has one solution. The graphs, that's where we have two lines, and that's where they intersect. For one solution, they intersect once. Okay, so just a quick diagram. We'll have some arrowheads. This would be the solution, that point where they intersect. Okay. Number two, describe the graphs of system of linear equations that has no solution. So if where the graphs intersect, where they two straight lines, they intersect once, that's one solution. Where they intersect no times, the graphs would have, we'll just say the graphs of these straight lines are parallel. I'll put the symbol for parallel. And then let's draw an example here. Right, two parallel lines. And then when you annotate two lines, you put like an arrowhead in the middle of it. That means that those two lines are parallel. We talked about that when we worked in transformations in Module 1. Okay, anyways, but there is this other type of solution, and that is this. So our title here, systems with infinitely many solutions. There's an infinite number of points, x and y, that satisfy both equations in the system. Okay. So number 3 says, consider the system of equations y equal to 3x plus 6 and y equal to, and then we have this grouping here, 3 times the quantity x plus 2, and that's all in parentheses. Okay. So number 3a says, complete the table of values for the system. We're going to use order of operations, so GEMDAS here. So at least in GEMDAS here, this tells us we are going to first multiply by 3 and then add 6. Versus here, right, we have this 3 that's being multiplied, but this x plus 2, that's a part of a group, and that is to add here. I'll put a underneath. So this actually tells us to add the 2 to the x value and then multiply by 3. We'll do this a couple of times, and then I'll kind of fill in the answers as we go on. So let's start with our first ordered pair. That is -2. So -2 here, -2 times 3 is -6. And then after that, I add -6 plus 6. -6 plus 6 is 0. If you take away 6 and then add 6, that is 0 there. And then let's go to the next one, 0. So if I plug a 0 in here, right, 3 times 0 is 0, and 0 plus 6, that's 6. All right, let's do a couple more. We're going to plug in a 2. Or if I plug a 2 in here in parentheses, 3 times 2 is 6, and 6 plus 6 is 12. All right, let's go through, and maybe one more. And that is 4. I will plug a 4 here. 3 times 4 is 12, and 12 plus 6 is 18. I'm going to give us the answer for the remaining ones, or you can pause the video here, try to figure it out. When we have this input of 8, after you multiply by 3 and add 6, you're going to get 30. This next one is 45. And if we plug in a 20, let's just do 20 here. Right, 3 times 20 is 60. And 60 plus 6 is 66. Okay, so we have this first column here. All we did, we plugged in a number, we multiplied it, and then added, and we got our final output. Here, or like we said, we're going to add first to 2, and then whatever that is, multiply by 3. So let's see that for this first one here. First one is -2. So I'll put a -2 in for x. -2 plus 2. -2 plus 2 is 0. And then now you do 3 times 0. 3 times 0 is 0. Okay. Next one is 0. I plug that in here. 0 plus 2 is 2. Right? What's 3 times 2? It's 6. All right. And you're more than welcome to pause the video, try to figure out the outputs of all these. But let's go through 2 more. All right, let's plug in a 2. Okay, 2 plus 2 is 4. 3 times 4, that's 12. And then finally, just one more before we kind of go over the answers. It's 8. Let's plug in an 8 here. 8 plus 2 is 10. What's 3 times 10? Ooh, whoops, I skipped 4. And well, 3 times 10 is 30, so I'll plug a 30 in here. Forgot to plug in 4. Let's do that. All right, we get a bonus. 4 plus 2 is 6, and 3 times 6, that is 18. Okay, let's cross this off. All right, again, you're welcome to try to figure out the last 2. Pause it as like some additional kind of YouTube practice. But the answers for these last 2, this is 45. If you plug a 20, 20 plus 2 is 22. 3 times 22 is 66. Okay. All right, so hopefully we noticed something, but let's go through B. It says, describe the equations that make up this system. What can you conclude about the number of solutions to this system of linear equations? As you may notice, right in the table for both these equations, y equal to 3x plus 6 and also y equal to 3 times x plus 2, they have the same exact numbers. Every one of these rows is exactly the same when we plugged in these varying inputs from the left. Okay, so we're going to say that the equations, I'll put EQ for equations, are equivalent, meaning that they're equal to each other or to one another. And I'll say each other are equal to each other. Okay, so every point on the graph, right, like an example of a point for the first one would be 418. This is the same point as what would be on the other one. This is also a 418. So every one of the points on the first equation is going to be on the graph of all the points on the second equation. This system, when they're all the same exact points, this is what we call is they have infinitely many solutions. Okay, so we can see that on here. But how does that look like on a graph? So literally what that is, you'll have one line here, and for 2 equations that have infinitely many solutions, at least on a graph, you'll have 2 lines exactly on top of each other. They're directly matching each other. So the same slope, same y-intercept on the coordinate plane, that's what it would look like. Okay. All right, so we talked about one solution. 2 lines intersect once, no solution. Those lines are parallel. They have no points that intersect. And then infinitely many solutions where they're just exactly the same thing, maybe written in a different way. Okay. Okay, so we took these 2 things, and we have 2 people, Arav and Victoria, solved it algebraically. So we're going to look at Arav's first thing. So what they both decided to do, since this says y equal to this expression, they set these 2 expressions equal to each other. We can see that here, right? 3x plus 6 and 3 times the quantity x plus 2. Okay, so what did they do here? So first of all, Arav decided to use the distributive property. That's where you multiply, right, 3 times x, which is 3x, and 3 times 2, which is 6. And then we have this thing. We're probably trying to move variables to one side. Let's say we move this to the left side, all variables, x is to the left side. We have a positive 3x, so we subtract 3x to both sides. This equals 0. And as we subtract it on the left side, you may notice, right, this is also equal to 0. So that looks kind of familiar from the last video. But here, what we have is we're bringing down these constant values. Before we even move constant values to either side, this right here is a true statement. Right, 6 is equal to 6. 6 Skittles is the same thing as 6 Skittles. Okay, so this tells us when it's a true statement, this is what we call is infinitely many solutions. I'm just going to put the infinity sign, I'm going to put the letters for Lie, infinitely many solutions. And then Victoria solved it a different way, right? She still did the same thing as Arav, using the distributive property, but she decided to work with the constants first. Maybe she tried to get this 6, positive 6 on the right side by subtracting 6. That's going to cancel out as well. What we have here, we probably want to move variables to either side, but they decided to just divide by the coefficient. Dividing this by 3, that would be 1x or just x. And this would also be 1x or just another x. Now, typically, when you solve it algebraically, if you ever have a true statement where the left side is exactly the same as the right side, you're actually done with the problem, right? Because it's a true statement that tells you that it's infinitely many solutions. We'll just put the infinity sign. Okay, so number 4, we're going to analyze that. It says, explain why both Arav's and Victoria's methods are correct, but have different solutions. So let's say both are correct. Let's just state that. The reason that they're both correct, so both are correct because, maybe I'll put comma, because both have a true statement. Right? Typically, we're used to like, at least in the last one, numerical statement where it's just numbers, but we even have the variable statement, right, of letters. X is equal to X, yeah, that's true. Banana is equal to banana, okay. If ever you get a true statement, you know you're done. And number 5, how do you interpret the final equation in each solution? Is the final equation always true, sometimes true, or never true? So is 6 equal to 6? Is that always, sometimes, or never true? This is always true. All right, 6 equal to 6, like that's not going to be sometimes true, right? It's always. And number 6, explain whether the system has one solution, no solution, or in an infinite number of solutions. I'm just going to underline this one here. It's an infinite number of solutions because all values of x make the equation, we'll abbreviate, true. Now what I mean by that is, like, you just look at the table. Every single one of these numbers made exactly the same thing on the right side, right? It didn't matter what we plugged in. Like I could plug in a random number, we could plug in 100. It's going to be the same thing. 3 times 100 is 300, plus 6 is 306. 100 plus 2 is 102. 300 times 102 is also 306, okay? It does not matter, right? So all values of x make the equation true. Okay, and we're going to get to this kind of second part of, we have 2 more pages on activity 3. So it says substitution with special systems. So we've talked about varying systems here where they have no solution or infinitely many solutions. That's what it means to be special there. Typically one solution is not special. One solution is like the norm. That's a normal thing. All right. So let's look at the situation. We'll write an equation. We'll talk about how we can interpret that. So it says Samson and Adrian help set up the booths at a fair. The organizers pay them each $7 per hour to carry the wood needed to build the various booths. Samson arrives at 7 a.m. and begins working immediately. Adrian arrives 90 minutes later and starts working. Okay. Let's say 90 minutes. That's going to be important. All right. So write a system of equations for this problem situation. Right. Remember, when you write this, typically it's going to be in slope-intercept form if we have some type of rate and some type of initial value where we begin. So for the first person, Samson, right, he's making $7 per hour. There's no starting amount that he's making. He doesn't like have like $50 in the bank. So y equal to mx is just gonna be y equal to 7x. This just says every single hour he's making $7 more. Okay, and then the second one for Adrian, right? Adrian's also making the same amount, but he arrives at work a little bit later, right? So I'm gonna write the equation. We'll talk about why is that the case. So his equation is y equal to 7 times x minus 1.5. Okay, if x represents, so what x is representing is hours. Since they start at 7, it's going to be hours since 7 a.m. Not to be confused with this 7 right here, right? Because that's $7 per hour. This is just time. And y is representing the amount of money made in dollars. So we'll just say money earned. So what is this representing here, right? If x is represented as hours, right? 90 minutes is not represented in hours, but we can represent that in hours, right? 60 of the 90 is 1 hour. And then we have 30 minutes left over. That's half an hour. So that's the 1.5, right? So he's working 1.5 hours less than Samson, who started at 7. So that's why it's x minus 7, right? Hours, 1.5 hours less than the number of hours since 7. And we have that in parentheses. Whatever that is, we'll multiply by 7. But we'll talk about like what do these two things represent. Okay. All right. B. Analyze the system of linear equations. How do you know, or what do you know about the solution of the system by observing the equations? I think from this we can say, right, if they're in slope-intercept form, right, we can say something about the slope. It looks like the slopes are the same, right? They're both 7 because they're making the same amount of money each, right, each hour that they work. The only thing that's a little bit different is the y-intercepts. Y-intercepts are different. Where they begin. They would be the same if they both start at the same exact time, but since Adrian is starting a little bit later, right, he's making less money. But what should that tell us about, before we even try to solve this, right? I want you to think of two lines that have the same slope, but they don't start on the same place on the y-axis. So let's draw two lines. These would be two lines that have the same slope and don't start in the same place on, let's say, the x and y axis. I'll draw the x and y axis here. Like maybe like this y-intercept is starting here, this y-intercept is starting here. So these two lines are parallel. P-A-R-A-L-L-E-L. So what that would tell us is that this is no solution because these lines do not intersect. Now let's prove that algebraically. So we're going to set these two equations equal to each other. I'm going to set 7x equal to 7 times x minus 1.5. So y equal to 7x, I'll just put 7x. And y equal to 7 times x minus 1.5. All right. Now I'm actually going to simplify this a little bit. We're going to have to distribute first. I'm going to keep this 7x on the left side. Let me draw a line. 7 times x is 7x. Now 7 times a negative 1.5, this is negative. 1, so 7 times 1 is 7. 7 times a half of 7 is 3.5. So 7 plus 3.5, that is 10.5. Or you could just take a calculator, you can multiply that. At this point, we can move variables to the left side. I would subtract 7x because we have a positive 7x. This would cancel out. And also, you know what? This would also cancel out. We would have 0 equal to negative 10.5. So this right here, we solved it, but let's answer number 4, which it says, does your result make sense? Right? This is this final equation is not true. It is a false statement. And we know when we have a false statement that it tells us that this is, we'll say the system has no solution, no soul. Okay. And then number 5, what is the result when you algebraically solve a system that contains parallel lines? We already answered that. It's just a false statement, right? False statement. So we had the 0 is not equal to 10.5, right? If you have $10.50, it's not the same thing as having $0, right? That's never gonna be true. Okay. All right. What I'd like for you to do For activity 3, I'll treat this as a you do here, but I'm going to help us get started on number 6. So try to solve this here. It says, so this is a different context, but you're going to do the same thing. Write an equation, right? Think about what does that equation represent, solve it algebraically, and so on. Exactly what we did on the previous page, so this is on page 341. Okay, it says on Monday night, the fair runs a special for the local schools. When you purchase tickets from the school, you can buy student tickets, abbreviate student, for $4 and adult tickets for also $4. I guess they're the same. And then here you buy 5 tickets and you also spend $20. Okay. So what we have here are kind of two things. We have number of tickets and we also have amount of money, right? I'm going to write the first equation. The first equation is, well, actually, let's define our variables. We'll say X is, let's say that is student ticket. And I'll say student tickets. And Y is adult tickets. Okay. So the first equation, to represent for number of tickets, we know that there's 5 tickets total. So we could say that the number of student tickets plus the number of adult tickets, this is equal to 5. And then if we want to think about this in terms of money, we know that it's $4 for a student ticket, $4 for an adult ticket, and total we spend $20. Okay. Now, if you were to solve both equations, so number 7, analyze the system of linear equations, how do you know, or what do you know about the solution of the system? By looking at the equations. What you can do here is you can actually solve each one. I'm going to take this first one. If I subtract x to both sides, I'm not going to show that step, but this will be y equal to, if I subtract it, it's going to be minus x plus 5. This is getting it into that first one into slope-intercept form. And this one here, it's a lot of work, but if you were to also, the second one, 4x plus 4y equal to 20, this would be y equal to negative x plus 5. It's exactly the same. I'm just going to describe it verbally. You'd have to subtract 4x to both sides. And then here, you'd have to divide every single thing by 4. So that's where you'd get this thing here. Anyways, I'd like for you to try to solve this algebraically. You're going to set both of these equal to each other and see what happens from there and answer the following questions. Okay. Anyways, I'll give you some time for that, but let's go to the assignment. So we're skipping activity 4, activity 5, talk to talk. Okay, your assignment. You don't have to do all these problems. On page 347, you have to choose one on number 1. So choose number 1, A, B, or C. You choose which one. Okay. On the back side, number 2, I want you to do A, B, and D. So we can cross off the other ones. And then 3, I don't want you to do A. I don't want you to do B. I just want you to do number 3, C, and D. So it's 1, 2, 3, 4, 5, and then 6. So 6 total problems here. Okay. All right. Anyways, let me know if you have any questions.